So, physical properties. A solid understanding of the attractive forces between particles is essential for understanding physical properties. So, rewatch the earlier video if you're not solid with your understanding of intermolecular forces. Alright, so this video focuses on boiling point. If you think of a pot of water that's boiling on the stove and you see the steam coming off the top of the pot, do you know the identity of that gas? Do you think, you know, the water is H2O? Do you think that that gas is H2, hydrogen gas, or O2, oxygen gas? What do you think? Hopefully, you're thinking there's a physical change happening as the water changes from liquid to gas. And in a physical change, there is no change in the composition of the particles. So in fact, that steam is H2O in the gas state. And so we have the evaporation of that water. The water particles move from liquid to gas state at 100 degrees Celsius. And that happens to be the boiling point of water. That's the temperature at which enough energy has been applied to start to overcome the attractive forces between the water particles. And so when you think of boiling or boiling point, think of the amount of energy that's needed to overcome the attractive forces between the particles that are undergoing the change of state. So can you fill in the blank beside BP for boiling point in this red statement? So stronger intermolecular forces would correspond to higher or lower boiling point. What do you think? Hopefully you're thinking higher boiling point. So if two friends are holding hands and they're holding them very strongly together and somebody's trying to, run through and break apart those people holding hands, then they're going to need a lot of force to do that. And if somebody's just holding on by their pinky finger to someone else, that's not a very strong attraction, and so it'll be much less energy would be required to overcome that. Okay, so we're going to use our knowledge of organic structure and attractive forces between particles to predict the relative boiling points of each set of compounds, and with an explanation. And so the first example here, it looks at methane and pentane. So I'd like you to pause the video, draw methane and pentane, and then predict the type of intermolecular force that each experiences, and then compare the relative strengths of those to predict the relative boiling point. What I mean by relative boiling point, just compare the boiling points. Do you think methane has a lower boiling point than pentane or a higher boiling point? That's the idea. Okay, check back in. Okay, so I began by figuring out the formulas of methane and pentane using CnH2n plus 2. And in writing the formula CH4, really I didn't draw methane, I just imagined the hydrogens around the carbon and left it as CH4. And for pentane, I drew the skeletal formula or line diagram. So the only bonds that are present here in both of these molecules are carbon-hydrogen bonds, and in the case of pentane, we also have carbon-carbon bonds. So you'll recall that those are nonpolar bonds. And if there's only nonpolar bonds in a molecule, then the molecule itself is definitely nonpolar, which leads it then to only possess London dispersion forces between molecules. And so you can see here that the London dispersion forces within a sample of methane are due to each molecule having 16 electrons. Now it also has protons obviously attracting electrons in neighboring molecules and vice versa. You'll notice with pentane, the London dispersion forces are due to 42 electrons. And if you recall from the previous video, more electrons indicate stronger London forces. And so pentane experiences stronger IMF, which leads to a higher boiling point. Now, pentane is still a gas at room temperature, as is methane. So if you have natural gas, a gas furnace or gas stove in your home, it's methane that is the gas that's being burnt. But pentane is also a gas at room temperature. but it does have a higher boiling point. So I'm leaving you with a bit of research here just to investigate how many carbons does the hydrocarbon, so a simple alkane, how many carbons, we know for sure from C1 up to C5, but maybe even further. So how is it hexane, heptane, octane? So how many carbons are there in the molecules that are gases at room temperature? And what about the liquids? How many carbons does the hydrocarbon chain have to have in order for the London forces to be strong enough to make that a liquid at room temperature? And so on for solids. So just do a quick internet check. You might have a prediction yourself, and then you can confirm. Let me know in class what you find out. Okay, part B. Working again with names of structures that you're familiar with. These were 3 of the isomers of C5H12. Pentane, 2-methylbutane, and 2,2-dimethylpropane. So I suggest you draw these structures and predict the IMF and then relative boiling points from there. Okay, so these 3 isomers are drawn now for you with skeletal formulas. They are all nonpolar molecules, and they all experience London dispersion forces only as their intermolecular forces, which those London forces will be of similar strength because they're C5H12. They all have the same number of electrons. And so what becomes the distinguishing factor at this point? Well, think about pentane here and a neighboring molecule of pentane being able to get close to that and experience London forces. Compared to the 2-methylbutane structure, because of this branch, it's harder for these molecules to get closer together. Oh, can you hear my dog? Just a minute, please. Okay, and the 2,2-dimethylpropane, you can see with its double branching here, it makes it even more difficult for these to be close together. And so what we're seeing here is a variation in surface area. So the surface area that pentane molecules experience London force interactions through is much higher. This is definitely a higher surface area. Okay, and we have a lower surface area of contact between the 2 molecules at this end, with 2-methylbutane somewhere in the middle. The higher surface area corresponds to stronger London forces, which therefore means a higher boiling point. And so at the right end of this example, we have the lowest surface area, therefore the lowest LDF, therefore the lowest boiling point. Okay, next example, part C. Give this a shot. Okay, so in analyzing these structures, the first thing to notice is that the hydrocarbon chains are all similar length. So because they're similar lengths, the LDF forces are going to be similar. And so we're looking really for the structural features that are different in these 3 molecules in order to see how those might impact the boiling point. So in the first structure, you can see there are only nonpolar bonds, and so that's a nonpolar molecule with London dispersion forces only. We're expecting a pretty low boiling point there. Now when you check the second structure, you'll see that polar C double bond O, which tells us that this molecule will not only have London forces, but the ability to dipole-dipole interact with another molecule like it. Whereas the far molecule on the right has a very polar OH bond, which now sets up the capacity for hydrogen bonding between adjacent molecules. And so the hydrogen bond being the strongest of the intermolecular forces corresponds then to this molecule will have the highest boiling point. Okay, next question, looking at D. Try that. Okay, so looking at example D, we see that polar C double bond O, which tells us this molecule will experience London forces as well as the ability to dipole-dipole interact with another molecule like it. The middle structure is a nonpolar molecule with London forces only. The fact that it doesn't have branches means it has a higher surface area than the third molecule in this question. And so the presence of the branches in 2,3-dimethylbutane on the right hand side here means that there will be a lower surface area and therefore weaker IMF. And so we see the lowest boiling point on the far right and the highest boiling point on the far left. Okay, last question. Okay, so in this last example, we see in the first structure this negative charge by the oxygen and the positive by the sodium. And so in fact, there's an ionic attraction here, an ionic bond, which is very strong, stronger than any of the other intermolecular forces. So we're expecting the highest boiling point here. Let's check the other two structures. I've circled the functional group here, and you may recall that this functional group experiences the dimer effect, which is an increased capacity for hydrogen bonding, which is going to raise the boiling point. Will it raise it higher than the ionic attraction? No. So we'll always classify the ionic attraction to be stronger than even the dimer effect here. And the far molecule on the right is certainly polar, but it's not able to hydrogen bond with itself. There is no hydrogen directly bonded to an oxygen, and so it will not be susceptible, it can't be susceptible to attraction from another molecule. Now, I say there it's the lowest boiling point on the right. Now, just a comment, these questions have all been answered comparing the boiling points of the molecules within the question. So it doesn't mean that the molecule on the right has a low boiling point, it's just the lowest of the three in this particular question. And that's it for boiling point.